Welcome to lecture 23. We are looking at 5.5, which is counting techniques. So for objective 1, solve counting techniques using the multiplication rule. For example 1, a fixed price dinner at a restaurant provided the following choices. For the appetizer, soup or salad. For the entree, you have a spaghetti with red sauce and meatballs, spaghetti with mozzarella cheese and brown butter, Parmesan chicken, or spaghetti with 3 cheese sauce. And then for dessert, you have the option of spumoni or vanilla. So, our question is, how many different meals can be ordered? Draw a tree diagram to list the possible choices. So, let's start with the appetizer. We have 2 choices, soup or salad. So let me go ahead and write that down here. We have soup or salad. After that, what choices could we possibly have? Then we have 1, 2, 3, 4 different choices for the entrees. And I am going to abbreviate these because they're pretty fancy to write. So let me go ahead with the abbreviations. Or spaghetti with red sauce, we'll do SR. For spaghetti with mozzarella cheese, we'll do SM. And then for Parmesan chicken, we'll do PC. And spaghetti with 3 cheese, we'll do ST. Alright, let's do that. So if, for example, you had decided to go with the soup first, and let me actually rewrite this a little higher. So your options would be spaghetti with red sauce, spaghetti with mozzarella cheese, Parmesan chicken, or spaghetti with the 3 cheese. There's the options there. And then same thing, if you had chosen the salad, you would still get the same 4 options for your entree. So many paths in life. Alright, and lastly, once you had that delicious entree, you could choose an ice cream, spumoni or vanilla. I'll write out vanilla, why not? Spumoni or vanilla. Spumoni or vanilla. Once again, spumoni or vanilla. Getting a little clustered here. Alright, then spumoni or vanilla once again for all of them. Alright, so these are the different options we have. So, how many possible meal options do we have? Well, we could count up the combinations by looking at the end of each one. So, this is one possible combination if we went through all 3 of these. So to count up the total possibilities, we're just going to go and count all of the ends that we see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different options. So if we did the tree diagram, we'd find out we have 16 different options. So 16 different meals can be ordered. Another way we could have done this is to just go ahead and do the number of options multiplied to each other. So we had 2 for the appetizer, 4 for the entree, and 2 for the dessert, which would be 2 times 4 times 2, which would end up equaling 16. So the tree diagram, or just multiply the different options together. So for the multiplication rule of counting, if a task consists of a sequence of choices in which there are P selections for the first choice, Q selections for the second choice, R selections for the third choice, and so on, then the task of making these selections can be done in P times Q times R, and however many options we have for the different ways. So for our problem, we had 2 for the for the salad or soup, Then we had 4 for our entree items, the spaghettis or the chicken. And then we had 2 for the ice creams, spumoni versus vanilla. We just multiplied them together. Now for example 2. The International Airport Transportation Association assigns 3-letter codes to represent all airport locations. For example, the code for Hawaiian International Airport is HNL. How many different codes are there possible? Well, let's see. What do we need? Well, we know we're looking for 3-letter codes, so we need 1, 2, 3 different options. How many different options do we have for each space? Well, for this space, we're looking at the number of letters we have in the alphabet, and there are 26 letters. So there are 26 options for the first space. Then for the second space, we're still allowed to use any letter possible. We could always have a double repeat. That wouldn't be a problem. So there's still 26 letters available. So we'll multiply that by 26. Once again, there's no restrictions on this other one. It could also be a repeat as the others. So once again, there are 26 options available, which would be 26 times 26 times 26, which equals 26 to the 3rd power, which comes out to 17,576 different code possible. So our answer would be there are 17,576 different airport codes possible. Canon neat. Now example 3. 4 members from a 14-member committee are to be randomly selected to serve as chair, vice chair, and secretary. The first person selected is the chair, the second person is the vice chair, and the third is the secretary. How many different committee structures are possible? Alright, so this one's going to be slightly different than the example above, and we'll see why in a second. Well, we know that there are 3 different chairs there are 4 different members, or chairs we're trying to fit. Actually, that's a typo. That should be fixed on your notes. There are 3 members that we're trying to pick. We have chair, vice chair, and secretary. So 3 possible chairs. 1, 2, 3. Very similar to the example above. We had 3 spaces. So the first time, we have a group of 14 people, right? There should be 14. I'm not going to write them all out. That's kind of a lot. So let's say there are 14 people. If you pick one of the people out and you decide to go ahead and plop him in the chair, what is the probability of how many options do we have for the first group? Well, there are 14 different guys, right? But once we've taken that person out, they're gone from the group, right? So the number of people in the group actually goes down from 14 to being 13. Which was different than the one above. The one above, we could use the same option for each spot, right? You could use H 3 times. The hard thing with people is once you take them out, or once you use them, they're not available for the other seat. You can't sit in 2 seats at one time. So once we've taken the first person out, 14 is gone. Now we only have 13. So if we take this person out and plop him in this chair, well, that once again changes the number of available people we have to fill the last space. So that's 13. Let me take away that dot. So now we no longer have 13 people. We only have 12. And once we take away 12 person, we would have none left, but those are all the seats that we needed to fill. So this is what happens when you can't use necessarily replacement. Alright, so now we have 14 times 13 times 12, which when we multiply all of that out gives us 2,184. Whoa! What does this mean? There are 2,184 different committee structures possible. So the main difference between these 2 problems, again, one of them, it didn't matter if you had repeating. You could have H 3 times and that doesn't matter. But for example 3, Bob cannot serve as the chair the vice chair, and the secretary. That is not possible. You need to have a different person for each spot, which is why the way we calculated it changed. So let's introduce a new form of notation. If n is greater than or equal to 0 is an integer, the factorial symbol n to the exclamation point is defined as follows. So, n factorial is actually what we would call it, means n times the number below n times the number down by 2n, so on until you reach 2 and then 1. And one other thing to note it, 0 to the factorial power, or 0 factorial, is going to equal 1, and 1 factorial also equals 1. Kind of strange. It's just talking about the different ways you can arrange numbers. So if you think about it, if you have one object, for example, let's say a candy. I don't know, is that what a candy looks like? Okay. If you have a candy, how many different ways can you arrange that piece of candy? There's only one way, it's right there. So that's the one way you can arrange that piece of candy. Another way of thinking about it, which is kind of weird, how many ways can you arrange nothing? Once. At least that's the way I heard it explained it to me. Kind of odd, but there we go. I'm sure you can look up further YouTube videos on how exactly that came about to be the definition there. So, for a mini example, 7 factorial is going to be 7 times the number smaller than 7, which would be 6, times the next number down from that would be 5, and so on. 4, 3, 2, 1, until we hit 1. Then we would multiply all of those numbers together. So that's 7 times 6 times 5 times 4 times 3 times 2 times 1. Let me type that in. 7 times 6 times 5 times 4 times 3 times 2 times 1. Ooh, big number. 5,040. That is what 7 factorial is. Alright, so for example 4, you have just been hired as a book representative for Pearson Education. On your first day, you must travel to 5 schools to introduce yourself. How many different routes are possible? Alright, so we have 5 different schools, so 1, 2, 3, 4, 5. Let's call them A, B, C, and D. So A, B, C, D, and E. These are the schools you need to visit. And you're going to visit them in different orders because you can only be at one school at a time. So if I was deciding what school I was going to pick for the first one, how many options do I have? 1, 2, 3, 4, 5 options. Well, let's say, for example, the first one you chose was A. Now for the next school. Since you've already gone to one of them, how many options are left? Just 1, 2, 3, 4 options are left. Let's say that was B. Okay, now you're going to the next school. How many options are left? Just 3. That school's over. How many options are left now? Only 2. And lastly, once that one's done, how many options are left? Just 1. So we'll multiply the options we have. And notice this actually looks like 5 factorial. And what is 5 factorial equal to? Well, 5 times 4 is going to be 20. Times 6. 5 times 4. 20 times 3 is going to be the 60. Then times 2 is going to be 120. And times 1 is just going to leave it at 120. So there are 120 different options. So how many different routes? There are 120 different routes. Oops, it's not a root, not like the tree root, the other kind of root. Alright, so solve counting techniques using permutations. Alright, by definition, a permutation is an ordered arrangement in which R objects are chosen from n distinct or different objects so that R is less than n and repetition is not allowed. So this is a key thing. Remember in the airport example, repetition was allowed. We were allowed to get H, H, and H. But we're looking at examples where repetition is no longer allowed. And the symbol NPR represents the number of permutations of our objects selected from n objects. A way to read this is n pick r. Alright, so number of permutations of distinct objects taken r at a time. So the number of arrangements of r objects chosen from n objects in which 1. The n objects are distinct or different. 2. Repetition is not allowed. 'Kind of like in that one example, if we had Bob, he cannot serve as the president and the vice president, or the chair and the vice chair. We need to have one person per seat. And then 3rd, order is important. Okay, this means, for example, the one that's first is important compared to having first somewhere else down the line. And this is given by the formula. NPR is going to be n factorial all over n minus r factorial. This is a very important formula for permutations. And once again, these are the criteria for permutations. So that's how you know if you're going to be using a permutation, if these different items show up in your problem. But for now, let's just focus on computing the permutations by themselves. So we're using 6 choose 4, or 6 pick 4. By the formula, my n value is 6. So let's write this down. N equals 6 and r is 4. So using our formula, we'll take 6 factorial divided by 6 minus 4 factorial. And let's see what this is going to be. 6 factorial all over 2 factorial. Well, if I write this out, I know that's 6 times 5 times 4 times 3 times 2 factorial divided by 2 factorial. These 2 factorials can actually cancel each other out. And we'll just be left with the 6 times 5 times 4 times 3, which is going to be, let's see, plopping that in our calculator, 6 times 5 times 4 times 3, 360. And the next one, go ahead, pause the video, try to do part B by yourself. So for part B, oddly, we have n is 4 and r is 4. So we have 4 objects and we're picking 4 of them. Let's see what we get. That's going to be 4 factorial all over 4 minus 4 factorial, which is going to equal 4 factorial all over 4 minus 4 is 0 factorial. Okay, let's see. Well, we might be tempted to say we're dividing by 0, so we can't keep going. But remember, 0 factorial is equal to 1. So this is just going to be 4 factorial over 1, which is going to be 4 times 3 times 2 times 1 divided by 1. And that's going to be 12 times 2, which is going to be 24. Alright, so tricky thing. Please note, 0 factorial is 1. Example 6. In how many ways can horses in an 8-horse race finish first, second, and third? Alright, so let's think. Does this problem fit what we have for permutations? Let's see, are the n objects distinct? We're talking about horses, so yes, the number of horses we have are distinct. They all have different names, personalities, and they are different beings. Part 2, repetition of objects is not allowed. Well, we're not going to be repeating the objects because we're looking at which ones finish first, second, and third. And also, for order is important, we are looking at one as being first, second, and third. So yes, it fits the permutations. So, let's see. N, what is the total that we're looking for? N is going to be 8 horses. And what are we picking? We're picking first, second, and third, so 3 options. So for our permutation, we're looking at n pick 3. That'll be 8 factorial all over 8 minus 3 factorial, which is going to be 8 factorial all over 5 factorial. And let's see, this is going to be 8 times 7 times 6 times 5 factorial all over 5 factorial. This is just a cheat way of sort of canceling, because I know the rest of them are going to be just 5, 4, 3, 2, 1. just like this. So we can cancel out all those extra numbers, and we're just left with 8 times 7 times 6. So 8 times 7, 56, times 6, 336. Almost wrote with my real pen here. Okay. And there we go. So, this is a word problem. So, how many ways can horses in an 8-horse race finish? The horses can finish in 336 different ways. Exclamation point, because it's extra exciting, right? Okay, so for objective 3, solve counting techniques using combinations. So a little different. We were looking at permutations, now we're looking at combinations. Alright, so what is different between these two? Well, by definition, a combination is a collection without regard to order. So this is where it changes. The other one we had to care about order. So for combinations, we're not caring about order, in which r objects are chosen from n distinct objects with r less than n, and without repetition. Okay, so a little different. It's not quite like the airport problem. And the symbol n choose r, this time with a C for combination, represents the number of combinations of n distinct objects taken r at a time. So for example 7, Keanu, Kelly, Tim, and Loke are going to play basketball. They will randomly select teams of 2 players each. List all of the possible team combinations. That is, list all the combinations of the 4 people. Keanu, Kelly, Tim, and Loke, taking 2 at a time. Okay, go ahead, pause the video, and try to write down all the different possible combinations. Alright, so hopefully you took a time to do that. Let's see, the possible combinations. We could have Keanu and Kelly. Then we could have Keanu and Tim. Then Keanu and Loke. Alright, let's see. Now let's look with Kelly. We could have Kelly Keanu, which we already did. We could have Kelly Tim. We don't have that one yet, so let's go ahead and write that down. Kelly Tim. Then we could have Kelly and Loke, which we don't have yet, so we'll write that one down. Okay, we looked at Kelly. Now let's take a look at Tim. So we could do Tim and Keanu, which we already have. We could do Tim and Kelly, which we already have. Or we could do Tim and Loke, which we don't have yet. So Tim and Loke. Now lastly, let's take a look at Loke. We could do Loke and Keanu. We already have that. We could do Loke and Kelly. We already have. How about Loke and Tim? And we already have that. So we have done all of the possible teams. And there we have our list of all possible teams. So the question is, what is 4 choose 2? Well, if we wrote them out like this, we could see how many different possibilities are there. There are 1, 2, 3, 4, 5, 6 different possibilities. So what is 4 choose 2? Well, 4 choose 2 is going to be 6. Now let's take a look at the criteria for combinations. So it's going to be a little different than permutations. Well, the combinations, the number of different arrangements of R objects chosen from N objects in which the N objects are distinct. Okay, so that's very similar to permutations. They shared this definition, or this criteria. Next, it says repetition of objects is not allowed. This is also the same for permutations. And lastly, it says order is not important. Okay, this is where it differs from permutations. So for combinations and permutations, they share the same 2 top criteria, but where they differ is the last one. If you care about the order, you're going to be using a permutation. If you do not care about the order, you'll be using a combination. That's the big basic difference. So what's the formula for combinations? It's similar. So if we're doing n choose r, we'll take n factorial and divide it by r factorial times n minus r factorial. Main difference, we have the r factorial down in the bottom because we do not care about the order. So let's take a look at example 8. Compute the following combinations. Actually, let me bring this down. Well, for this, what is n? N is going to be the 7, and r is 3. So filling this out, we get 7 factorial divided by 3 factorial times n minus r, which is going to be 7 minus 3 factorial. That comes out to 7 factorial all over 3 factorial times 4 factorial. And what will that be? 7 factorial is going to be 7 times, and now I want to try to find a way to cancel here, so that's what I'm thinking. 7 times 6 times 5 times 4 factorial, all over 3 factorial times 4 factorial. Those factorials cancel, and I'm just left with the 7 times 6 times 5 all over 3 factorial, which simplifies that to 3 times 2 times 1. Okay, and when I do this, I can cancel the 6 with the 3 and the 2, and I'm just left with 7 times 5, which is 35. So, you may be able to notice I like to avoid using the calculator, if possible, by simplifying. If you don't want to do that, you could go ahead and plop all of that in your calculator, or you could do the simplifying and just get that as your answer. Alright, go ahead and try part B by yourself. Well, hopefully you tried that off by yourself. So now we have n is 6 in this problem, and r is 2 for this one. So using our formula, we'll get 6 factorial divided by 2 factorial, times 6 minus 2 factorial equal to, well, that's 6 factorial all over 2 factorial times 4 factorial. Let's see if I can do any of my canceling. So 6 factorial is going to be 6 times 5 times 4 factorial, all over 2 factorial times 4 factorial. The 4 and 4 cancel, and I'm left with 6 times 5 all over, and 2 factorial is just going to be 2 times 1, which is just 2. The 2 and the 6 can cancel, and I'm left with 3. So I have 3 times 5, which is going to be 15. Alright. I find the canceling fun to do. If you don't like to do it, pretty much the work I'll be looking for example, on an exam, would be this, and then up to this step. And if you choose to do this step on the calculator and you skip right to there, that's fine. But the steps I'll be looking for on the exam would be these to that one. Example 9. How many different simple random samples of size 7 can be obtained from a population whose size is 21? Well, we can go ahead and use the combinations here. So the combination, we have 21 is our n, and we're choosing 7. So 21, choose 7. In our formula, that's going to be 21 factorial all over 7 factorial times 21 minus 7 factorial. That'll be 21 factorial all over 7 factorial times 21 minus 7, which is 14 factorial. Alright, so 21, so that's going to be 21 times 20, 19, 18, 17, 16, 15, and 14 factorial. So this is where it starts to be not quite as fun to do all the canceling. Then 7 factorial times 14 factorial. The 14s cancel each other out. And then we're left with the 7 factorial. So I'm going to go ahead and show my work moving over to here with the arrow, so my readers can follow my work. And then 21 times 20 times 19 times 18 times 17 times 16 times 15. And if you have this function in your calculator, that works awesome as well. So then we have the 7 factorial, which is 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, plugging that into the calculator, we get 116280. Alright, so the larger the numbers get, the canceling's not quite as fun anymore, so if you go ahead and plug it into your calculator as usual, I just look for these two steps, and then your number. As well as this step right there. Okay, so, Objective 4. Solve counting techniques. That should actually say solve counting problems. I should have changed that in your notes. Alright, so solve counting problems using permutations with non-distinct items. For example 10, a DNA sequence consists of a series of letters representing a DNA strand that spells out the genetic code. There are 4 possible letters, A, C, G, and T, each representing a specific nucleotide, I'm not certain if that's how I say it, base in the DNA strand. Adenine, cystosine, guanine, and thymine, respectively, which I hope I said right. If not, I probably butchered it. Alright, so how many distinguishable sequences can be formed using 2 A's, 2 C's, and 3 G's, and 1 T? Alright, let's get a visual going here. Each sequence that we form will have 8 letters. Okay, so to construct each sequence, we need to fill in 8 positions with the 8 letters. How do I know 8 letters? Because we have 2 plus 2 plus 3 plus 1, which gives us 8 letters total. We have 8 letters. So let's go ahead. We have 1, 2, 3, 4, 5, 6, 7, 8 positions. Okay. So this process is going to consist of, let's see, how many different tasks? We need 1, 2, 3, 4 different tasks. So for task 1, we're choosing the 2 A's, or the position for the 2 A's. And then task 2, we're going to choose the 2 C's. And then task 3, we're going to choose the 3 G's. And lastly, task 4, we're going to choose the 1 T. So how would we do task 1? Well, this would be 8C2. We're doing combinations over permutations because the order does not matter. Okay, so that would be how we would do task 1. Task 2, well, 2 of the spaces are taken. So that means we have 6 opportunities and we're going to choose from it 2. Okay, that means these 2 spaces are gone for task 3. For task 3, we have 4 options. And from that we're choosing 3. And lastly, we have 1 space. So for this one, we have 1, and we're choosing only 1 for the 1T. Okay, so this is how we find our answer here. So we're going to go ahead and use the multiplication rule to find the number of possible sequences. And by doing that, we multiply all of them together. So we have 8 choose 2 times 6 choose 2 times 4 choose 2, 3, times 1 choose 1. Let me write that out on the side actually with a little more space for that. Let's see. Write it over here. Looks good. Let me erase the extra. Okay. So what would this look like if I wrote this out with the combinations? Well, for 8 choose 2, that's going to be 8 over 8 factorial over 2 factorial times 8 minus 2 factorial times 6 factorial all over 2 factorial times 6 minus 2 factorial times 4 factorial all over 3 factorial times 4 minus 3 factorial. And lastly, the 1 factorial all over 1 factorial times 1 minus 1 factorial. All right. Let me move this up a teeny bit for the work. Did not give myself the most space possible for this problem. Okay. The 8. Okay, so now for simplifying this, we have 8 factorial all over 2 factorial times 6 factorial times 6 factorial. Oops, it's not looking like an exclamation. All over 2 factorial times 4 factorial times 4 factorial all over 3 factorial times the 1 factorial times the 1 factorial all over 1 factorial times 0 factorial. Whew! Now let's see what we can cancel. Well, the 6 and the 6 cancel, the 4 and the 4, and then, of course, I guess the 1 and the 1. And that leaves us with 8 factorial all over 2 factorial times 2 factorial times 3 factorial times the 1 factorial and the 0 factorial, which is just 1. And that comes out to be 1,680. So my answer would be there are 1,680 possible sequences. Now let's look at permutations with non-distinct items. So the number of permutations of n objects, of which n sub 1 are one of a kind, n sub 2 are second of a kind, and n sub k are the kth kind, is given by the formula n factorial over n sub 1 factorial times n sub 2 factorial times so on. So we get n sub k factorial, where n is going to be the different items added together. For example, 11. How many different vertical arrangements are there of 9 flags if 4 of the flags are white, 3 are blue, and 2 are red? Alright, so because these are non-distinct items and the order does matter, we're going to use a formula for finding the number of permutations. So what are we trying to find? Well, we have n equals how many objects? Let's see, 9 objects. Of which, let's see, n sub 1 is going to be the 4, and the 4 flags that are white. N sub 2 is going to be the 3, which are blue. And then n sub 3 is going to be the 2, which are red. So I'll go ahead and put this in parentheses. We have the white, blue, and red. Now using our formula from above, this is going to end up being 9 factorial all over 4 factorial times 3 factorial times 2 factorial. Okay, and one thing to note real quick, forgot to check, n should equal all of these values added up, which would be the 4 plus the 3 plus the 2, which does equal the 9. So have to remember, make sure that works out there when you're writing this out. Okay, so what is this going to be? Well, this will be 9 times 8 times 7 times 6 times 5 times 4 factorial all over 4 factorial times 3 factorial times 2 factorial. These factorials cancel out. The 3 factorial ends up equaling 6, which will cancel with the 6. And the 2 factorial is just going to be 2, which we can cancel with the 8 to get 4. So we'll get, let me erase a little bit something for space here. Equals 9 times 4 times 7 times 5, which equals 1,260. Oops, wrong spot. So our answer would be, there are 1,260 possible arrangements. Period. Okay, let's take a look at Objective 5, which is the last objective for this section. So compute probabilities involving permutations and combinations. Alright, so example 12. In the Illinois lottery, an urn contains balls numbered 1 through 52. From this urn, 6 balls are randomly chosen without replacement. For a $1 bet, A player chooses 2 sets of 6 numbers. To win, all 6 numbers must match the chosen from the urn. The order in which the balls are picked does not matter. What is the probability of winning the lottery? Okay, so the one thing is, should I choose permutations or combinations? And remember, the main difference was combinations order does not matter, but permutations it does. Now, for this problem, the order does not matter, which I know means you're going to be using combinations. Okay. So we're looking at a combination. What is the sample space? What is n? Or the sample size? N is going to be 52. And then what are we choosing? From that, we're choosing 6 items. So 52, choose 6. So which means that's going to be 52 factorial over 6 factorial times 52 minus 6 factorial, which will be 52 times 51 times 50 times 49 times 48 times 47 times 46 factorial, all over 6 factorial times the 46 factorial. These guys cancel out, and then, let's see, putting those into a calculator, we get 20,358,520. Okay, so we found that part. And what do we know? Well, that's just for one of the sample size, remember, because you have 2 options for 6 numbers. So each ticket has 2 chances of winning. Let E, event, of winning. So then, if we're looking at the probability of our ticket winning, that's going to be the number of our event over the number of the sample space. And the number of our event is going to be 2, because we have 2 chances there, divided by our total number here, which is going to be the sample space. Oh, I should have indicated that above. My sample space is going to be n of s. Oops, wrong pen. Divided by the 20,358,200 Putting that in the calculator, we get 0.00. How many zeros is that? 0.000098. Ooh, that got messy. That's supposed to be 7 zeros, so 0.1, 2, 3, 4, 5, 6, 7, 9, 8. So, well, that is approximately about, if I was to write this as a fraction, that would be about 0.1234567, which we could write as 1 over, with 7 zeros, 1, 2, 3, 4, 5, 6, 7. Oops, I did the commas in the wrong place. 7 zeros. So that means that there is a 1, or about a 1 in 10,000 chance of winning the Illinois lottery. That is insane. But technically there's still a chance. So go for it if you want. Alright, so example 13, the last example for this section. A shipment of 120 fasteners that contains 4 defective fasteners was sent to a manufacturing plant. This sounds familiar. The plant's quality control manager randomly selects and inspects 5 fasteners. What is the probability that exactly one of the inspected fasteners is defective? Alright, so what are we looking for? We're looking for the probability of 1 defective fastener. And how do we find that? Well, we want to find the number of ways to choose the defective fastener, one defective fastener, and divide that by the total number in our sample size. Well, the total number in our sample size, let's see, are we thinking about order matters or order doesn't matter? Well, in this problem, order does not matter, so we're going to use combinations for C. So, from 120 fasteners, we are choosing 5. So 120, choose 5. Okay, that was pretty straightforward. Now we need to figure out the number of ways to count for the one defective fastener. Well, what is the probability of picking 1 out of the possible 4 ones? Well, we would just write that down. I don't know what it is, but from 4 defective, that's the probability of choosing 1. And then that means we need to multiply this by the probability of the other 4 not being defective. Well, the other 4 not being defective would be, we're choosing from out of 116. How did we get 116? Well, 120 minus the 4 defective ones would be 116. So these are the non-defective. Okay, so we'll go ahead and do that. So from the 116, you end up choosing 4 that are non-defective. So this is the probability for that 1 that is picked that is defective. And then the other probability, we're multiplying it by the probability of picking the other 4 that are not defective. Okay, so we just happen to pick 1 that's defective and the other 4 are not. Alright, so multiplying that out, so working this out on the side, you'll end up with 28,640,980 divided by, working that out, 190,578,024. So you can go ahead and plug these into your calculator to find that, or into Wolfram Alpha. There's also the technology on page 281. Page 281, if you want to take a look at that. Okay, now dividing this out, we'll get approximately 0.1503. So, if I wanted to translate this, once again on the side, I'm going to take a look. 0.1503 is approximately 0.15, which we could write as 15 out of 100. So this is saying that if we selected 5 fasteners 100 times, we would expect about 15 of the samples to have exactly 1 defective fastener. Okay, so that's just the way of interpreting that on the side. I find it easiest to interpret when I turn it into a fraction. That way I can see the 15 out of 100. Alright. Okay, that is it for this section. For directions on using these different items, go ahead and read page 281 of your textbook or shoot me an email. Alright, that is it for this section. Please email me if you have any other questions.